Well, hello, welcome back to our course on system engineering, ENGR 345. And for this lecture, we're going to go over chapter 2 and talk about structure of complex systems, something that's very common with systems engineering. So let's just kind of give a perspective to start out with here, thinking about what a system engineer is like versus what it is like for a subject matter experts. So we're going to think about the system elements and interfaces, the needs for a system engineer to attain a broad knowledge of several interacting disciplines involves the development of a complex systems, raises a question of how deep that understanding needs to be. Clearly, it cannot be as deep as the knowledge possessed by the specialists in these areas, yet it must be sufficient to recognize such factors as program risk, technological performance limits, and interfaces requirements, and to make trade-offs analyzing among these alternatives. Obviously, the answer depends on specific cases. However, it is possible to provide an important insight by examining the structural hierarchy of modern systems. Such an examination reveals the existence of identifiable types of building blocks that make up the large majority of systems and represents the lower working level of technical understanding that the system engineer must have in order to do the job. This is a level at which technical trade-offs affecting system capability must be worked out, and at which interface conflicts must be resolved in order to achieve a balanced design across the entire system. The nature of these building blocks is the context as fundamental system elements, and their interfaces and interactions are discussed in the following sections that we'll cover in this lecture. So basically, you can think about what I like to think of as a system engineer as a mile wide and relatively modest in its depth, but enough, as I just mentioned, versus a subject matter expert is supposed to have an entirety, a broad sense of what is the drivers in that particular area. So what about the hierarchy of complex systems? In order to understand the scope of systems engineering and what a system engineer must learn to carry out the responsibilities involved in guiding the engineering of a complex system, it is necessary to define the general scope and structure of that system. Yet the definition of a system is inherently applicable to different levels of aggregation of complex interacting elements. For example, a telephone substation with its distributed lines to the area that it serves can be properly called a system. Hotel and office building switchboards with their local lines may be called a, quote, subsystem, and the telephone and instruments may be called components of the system. At the same time, the substation may be regarded as a subsystem of the city telephone system, and that in turn to be a subsystem of the national telephone system. In another example, a commercial airline certainly qualifies to be called a system, and its airframe, engines, controls, and so on being subsystems. The airliner may also be called a subsystem of the air transportation system, which consists of the air terminal, air traffic control, and other elements of the infrastructure in which the airline operates. Thus, it is often said that in every system is a subsystem of a higher level system, and every subsystem may itself be regarded as a system. The above relationships have given rise to terms such as supersystems to refer to overarching systems like the wide area telephone system and the air transportation system. In network military system, the term system of systems has been coined to describe integrated distributed sensor and weapon systems. This nomenclature has migrated to the commercial world as well. However, the use and definition of the term vary by area and specialty. In terms of a model of complex system, while learning the fundamentals of system engineering, the ambiguity of the scope of the system may be confusing. Therefore, for the purpose of illustrating the typical scope of systems engineers' responsibility, it is useful to create a more specific model of a typical system. As will be described later, the technique of modeling is one of the basic tools of system engineering, especially in circumstances where unambiguous and quantitative facts are not readily available. In this present instance, the technique will be used to construct a model of a typical complex system in terms of its constituent parts. The purpose of this model is to find a relatively simple and readily understood system architecture, which can serve as a point of reference for discussing the process of developing a new system and the role of system engineering throughout the process. While the scope of this model does not extend to that of a supersystem or a system of systems, it is representative of the majority of systems that are developed by an integrated acquisition process. By their nature, complex systems have a hierarchical structure in that they consist of a number of major interacting elements, generally called subsystems, which themselves are composed of more simple function entities and so on, down to primitive elements such as gears, transformers, or light bulbs, usually referred to as parts. Commonly used terminology for the various architectural levels in the structure of a system is confined to the generic system and subsystem designation for the uppermost levels and parts for the lowest. For reasons that will become evident later in this lecture, the subsystem model as defined in this book will utilize two additional intermediate levels, which will be called components and subcomponents. While some models use one or more of these intermediate levels in their representation of systems, these 5 have proven to be sufficient for the intended purpose. In this table, we're illustrating the above characterization of the hierarchical structure of the system model. This diagram shows 4 representative subsystem types employing advanced technology. They are listed horizontally, and successive levels of subdivisions with each systems are arranged vertically. So hopefully you'll find something that is in the area of engineering that you find interesting. Well, what about knowledge domains? In describing the various levels in the system hierarchy depicted in the figure, it was noted previously that the term system, as commonly used, does not correspond to a specific level of aggregation or complexity. It must be understood that the systems may serve as part of a more complex aggregation or supersystems, and subsystems may themselves be thought of as systems. For the purpose of this ensuing discussion in this lecture, this ambiguity will be avoided by limiting the use of the term system to those entities that 1, possess the properties of an engineered system, 2, perform a significant useful service with only the aid of human operators and standard infrastructure, for example, the power grid, highways, fueling stations, communication lines. According to the above conditions, a passenger aircraft would fit the definition of a system, as would a personal computer with its normal peripherals of input and output, keyboard, display, and so on. The first subordinate level in the system hierarchy, as shown in the previous table, is appropriately called a subsystem, and that has conventional connotation of being a major portion of the system that performs a closely related subsystem, related subset of the overall system functions. Each subsystem may in itself be quite complex, having many of the properties of a system except the ability to perform a useful function in the absence of the companion subsystems. Each subsystem typically involves several technical disciplines, for example, electronic, mechanical. The term component is commonly used to refer to a range of mostly lower level entities, but in the textbook, as well as what we're going to talk about here in this lecture, the term component will be reserved to refer to the middle level of system elements described above. Components will often be found to correspond to configuration items. called CIs for short, in government system acquisition notation. The level below the component building blocks is comprised of entities referring to subcomponents that perform elementary functions and are composed of several parts. The lowest level comprised of parts represents elements that perform no significant function except in combination with other parts. The great majority of parts come in standard sizes and types and can usually be obtained commercially. In terms of adaptive systems in developing responsiveness in each level of the system model, functionality and interactions are constantly influenced by external forces. Adaptive systems change behavior in response to their environment. They are dynamic systems able to evolve to continue to achieve their goals, objectives, and requirements. While similar to agile systems discussed earlier, adaptive systems are often related to natural, human, or social systems. The design and development of adaptive systems must accommodate indirect effects on components and system building blocks, as well as incorporate learning behavior based on use with autonomous-like characteristics. System engineers should also consider adaptive change with artificial systems, artificial intelligence system, neural networks, advanced evolutionary software elements, and related components with complex behaviors. When these building blocks support a complex system, they may be many independent elements or agents that interact at each system level, leading to emergent outcomes that are often difficult to predict by looking at the individual interactions. Hence, the systems engineers recognize this element of complexity as the overall systems are designed and developed. In terms of the domains of the system engineer and design specialist, from the above discussion, the hierarchical structure of engineering systems can be used to define the respective knowledge domains of both the system engineer and the design specialist. The intermediate system components occupy a central position in the system development process, representing elements that are, for the most part, products fitting with the domain of industrial design specialists who can adapt them to a particular application based on a given set of specifications. The proper specifications of components especially define performance and ensure compatible interfaces is the particular task of system engineering. This means that the system engineer's knowledge must extend to the understanding of the key characteristics of components from which the system may be constructed, largely through dialogue and interaction with the design specialist, so that he or she may select the most appropriate types and specify their performance and interfaces with other components. Well, we're showing in this figure the respective knowledge domains of the system engineer and design specialist using the system hierarchy defined above. It shows that the system engineer's knowledge needs to extend from the highest level down system and in its environment down through the middle level of primary system building blocks or components. At the same time, the design specialist knowledge needs to extend from the lowest level of a part up through the component level, at which point the two knowledge domains overlap. This is the level at which the system engineers and the design specialists must communicate effectively. So that's going to be something that's important that you want to make sure that actually takes place. So they communicate effectively, identify and discuss technical problems, and negotiate workable solutions that will not jeopardize either the system design process or the capabilities of the system as a whole. The horizontal boundaries of these domains are deliberately shown as continuity lines in the figure to indicate that they should be extended as necessary to reflect the composition of the particular system. When a subcomponent or part happens to be critical to the system operation, the system engineer should be prepared to learn enough about its behavior to identify its potential impact on the system as a whole. This is frequently the case in high-performance mechanical and thermal mechanical devices such as turbines and compressors. Conversely, when the specified function of a particular component imposes unusual demands on its design, the design specialist should call on the system engineer to re-examine the system level assumptions underlying the particular requirement. Next, let's think about the system building blocks. Using this system model provides system engineers with a simple method of partitioning a system along a functional and physical dimension, understanding that the functional aspects of the system, then partitioning the system into physical hierarchy. Each dimensional description of the system can then be decomposed into elements. Below, what we'll talk about next is the description of these two categories of building blocks and a recommended set of elements used in each of the components that will be characterized. So first of all, for functional building blocks, thinking of the functional elements, the three basic entities that constitute the media on which information operates are information, the content of the knowledge and communication material, the substance of the physical objects, and energy, which energizes the operation and movement of all active system components. Because all system function involves a purposeful alteration in some characteristics of one or more of these entities, the latter constitutes a natural basis for classifying the principal system functional element. Since the information elements are more than twice as populous as the material and energy entities among the system functions, it is convenient to subdivide them into two classes. One, elements dealing with their propagating information, for example, radio signals, to be referred to as signal elements, and two, those dealing with stationary information like computer programs, to be referred to as data elements. The former class is primarily associated with sensing and communication, and the latter with analysis and decision processing. The result in a total of four classes of the system functional elements. One, signal elements, which sense and communicate information. Two, data elements, which interpret, organize, and manipulate information. Three, material elements, which provide structure and transformation of material. And four, energy elements, which provide energy and motive power. To provide a context for acquainting each of you with the significant design knowledge peculiar to each of these four broad classes of functional elements, a set of generic functional elements has been defined that represent the majority of important types for each class. To make the selected elements self-consistent and representative, three criterion may be used to ensure that each element is neither trivially simple nor inordinately complex and has wide application. One's significance: each functional element must perform a distinct and significant function, typically involving several elementary functions. Two, singularity: each functional element should fall largely within the technical scope of a single engineering discipline. Three, commonality: the function performed by each element can be found in a wide variety of system types. In configuring the individual functional element, it is noted that regardless of the primary function and classification, their physical embodiments are necessarily built of material, usually controlled by external information and powered by electricity or some other source of energy. Thus, a television set whose main function is to process information is a form of radio frequency signal into information in the form of a TV picture, and sound is built of materials powered by electricity and controlled by user-generated information inputs. Accordingly, it should be expected that most elements in all classes would have information energy inputs in addition to their principal processing inputs and outputs. So let's think about those system functional elements. The above process converges on a set of 23 functional elements, 5 or 6 in each class. These are listed in the middle column of this table. The function of the class as a whole is shown in the left column, and the applications that might embody this individual elements are listed in the right column. It should be noted that the above classification is not meant to be absolute, but is established solely to provide a systematic and logical framework for discussing the properties of systems at the level of importance to system engineers. Fundamentally, the functional design of any system may be defined by conceptually combining and interconnecting the identified functional elements along with perhaps 1 or 2 very specialized elements that might perform a unique function in certain systems applications, as well as to logically define the desired system capabilities from the available system inputs. In effect, the system inputs are transformed and processed through the interconnection function to provide the desired system outputs. So this is the first part of that, and now we can be thinking about the component design elements. The physical building element components. First, let's think about the components themselves. System physical building blocks are the physical embodiment of the functional elements consisting of hardware and software. Consequently, they have the same distinguishing characteristics of significance, singularity, and commonality, and are at the same level in the system hierarchy, generally 1 level below a typical subsystem. And the 2 elements above apart, they can be referred to as component elements or simply components. The classes into which the component building blocks have been categorized are based on different design disciplines and technologies that they represent. In total, 31 different component types were identified and grouped into 6 categories, which we're showing in this table. The table lists the category, components, names, and the functional elements with which it is associated. As in the case of the functional elements, the components' names are indicative of the primary function, but in this case represent things rather than processes. Many of these represent devices that are in widespread use. The system engineer's concern with the implementation of the functional elements within components is related to a different set of factors than those associated with the initial functional design itself. Here, their predominant issues are reliability, form and fit, compatibility with the operational environment, maintainability, producibility, testability, safety, and cost, along with the requirements that product design does not violate the integrity of the functional design. The depths of the systems engineer's understanding of the design of the individual components need to be extended to the place where the system level significance of these factors may be understood and any risk, conflicts, and other potential problems addressed. The required extent and nature of such knowledge varies widely according to the type of system and its constitution. A system engineer dealing with an information system can expect to concentrate largely on the details of the software and user aspects of the system, while considering mainly the external aspects of the hardware components, which are usually standard, always paying the special attention to the components' interfaces. At another extreme, an aerospace system, such as an airplane, consists of a complex and typically non-standard assembly of hardware and software operating in a highly dynamic and often adverse environment. Accordingly, an aerospace systems engineer needs to be knowledgeable about the design of system components to a considerably more detailed level so as to be aware of the potentially critical design features before they create reliability, producibility, or other problems during the product engineering, test, and operational stages. Well, next, let's talk about system building blocks and focus on the common building blocks that are there. An important and generally unrecognized observation resulting from an examination of the hierarchical structure of a large variety of systems is the existence of an intermediate level of elements of types that recur in a variety of systems. Devices such as signal receivers, data displays, torque generators, containers, and numerous other perform significant functions used in many systems. Such elements typically constitute product lines of commercial organizations, which may configure them for the open market or customize them to specifications to fit a complex system. So we have some previous tables that got into this that take the above elements and show how they're situated at the third or middle level and are referred to by the name components. And then we also see that it is noted that one or more up through the hierarchy of a system element level, the functions performed by those in the middle or component level are the first that provide a significant functional capability, as well as being found in a variety of different systems. For this reason, the types of elements identified as components in the table were identified as basic system building blocks. Effective system engineering therefore requires a fundamental understanding of both the functional and physical attributes of these ubiquitous system constituents to provide a framework for gaining an elementary knowledge based on system building blocks. A set of models has been identified to represent common occurring system components. And in this section is devoted to the derivation, classification, and in interrelationships and common examples of the defined system building blocks. In terms of the application of system building blocks, the system building blocks model described above may be used in several ways. One, the categorization of fundamental elements into 4 classes of signal, data, material, and energy elements can help suggest what kind of actions may be appropriate to achieve required operational outcomes. 2, identifying the classes of functions that need to be performed by the system may help group the appropriate functional elements into subsystem and thus facilitate functional partitioning and definition. 3, identifying the system functional building blocks may help define the nature of the interface within and between subsystems. And 4, the interrelationship between the functional elements and the corresponding ones or more physical implementations can help visualize the physical architecture of the system. And then the last 2, the 5, the commonly occurring examples of the system building blocks may suggest the kind of technology appropriate to their implementation, including possible alternatives. And 6, for those specialized in software and unfamiliar with hardware technology, the relatively simple framework of 4 classes of functional elements and 6 classes of physical components should provide an easily understood organization of hardware domain knowledge. For the system environment, the system environment may be broadly defined as everything outside of the system that interacts with the system. The interaction of the system with the environment form the main substance of the system requirements. Accordingly, it is important at the onset of system development to identify and specify in detail all the ways in which the system and its environment interact. It is a particular responsibility of the system engineer to understand not only what these interactions are, but also their physical basis to make sure that the system requirements accurately reflect the full range of operating conditions. For system boundaries, to identify the environment in which a new system operates, it is necessary to identify the system's boundaries precisely. That is, to define what is outside the system and what is inside the system and what is outside. Since we are treating systems engineering in the context of a system development project, the totality of the system will be taken as that of the product to be developed. Although defining the system boundaries seems almost trivial at first glance, in practice it is very difficult to identify what is part of the system and what is part of the environment. Many systems have failed due to miscalculations in the assumptions about what is internal and what is external. Moreover, different organizations tend to define boundaries differently, even with similar systems. Fortunately, several criteria are available to assist in determining whether an entity should be defined as part of a system. Development control. Does the system developer have control over the entity's development? Can the developer influence the requirement of the entity, or are requirements defined outside of the developer's sphere of influence? Is funding part of the developer's budget, or is it controlled by another organization? Operational control. Once fielded, will the entity be under the operational control of the organization that controls the system? Will the tasks and missions be performed by the entity be directed by the owner of the system? Will another organization have functional control at times? Functional allocation. In functional definition of the system, is the systems engineer allowed to allocate functions to the entity? Unity of purpose. Is the entity dedicated to the system success? Once fielded, can the entity be removed without objection by another entity? System engineers have made mistakes by defining entities as part of the system, when in fact the span of control, as understood by the above criteria, was indeed small. And typically, either during development or operations, the entity was not available to perform its assigned functions or tasks. One of the basic choices required early is to determine whether human users or operators of a system are considered part of the system or are external entities. In a majority of the cases, the user or operator should be considered external to the system. The system developer and owner rarely have sufficient control over operations to justify their inclusion in the system. When operators are considered external, the system engineer and the developer will focus on the operator interface, which is critical to complex systems. From another perspective, most systems cannot operate without the active participation of human operators exercising decisions and control functions. In a functional sense, the operators may well be considered to be integral parts of the system. However, to be the system engineer, the operators constitute elements of the system environment and impose interface requirements that the system must be engineered to accommodate. Accordingly, in our definition, the operator will be considered to be external to the system. As noted earlier, many, if not most, complex systems can be considered as part of a larger system. An automobile operator on a network of roads is supported by an infrastructure of service stations. However, these are not changed to suit a new automobile. A spacecraft must be launched from a complex gantry, which performs the fueling and flight preparation functions. The gantry, however, is usually part of the launch complex and not part of the spacecraft's development. In the same manner, the electrical power grid is a standard source of electricity, which a data processing system may utilize. Thus, the super systems identified in the above examples need not be considered in the engineering process as part of the system being developed, but as an essential element in the operational environment. and to the extent required to assure that all interface requirements are correctly and adequately defined, system engineers must also become involved in interface decisions affecting design of both their own and interfacing system. In the example of the spacecraft launched from a gantry, some changes to the information handling and perhaps other functions of the gantry may well be required. In such instances, the definition of common interfaces and any associated design issues would need to be worked out with the engineers responsible for the launch complex. Next, let's go ahead and consider the context. For system boundaries, we want to be thinking about the context diagram. So an important communication tool available to the system engineer is the context diagram. This tool effectively displays the external entities and their interactions with the system and instantly allows the reader to identify those external entities. We'll have some use case diagrams when we get into model-based system engineering, which will be another way of conceiving this as well. So in this figure, it shows a generic context diagram. The type of diagram is known as a black box diagram, in that a system is represented by a single geographic figure in the center without any details. Internal components or functionality is hidden from the reader. The diagram consists of three elements. One, external entities. These constitute all entities in which the system will interact. Many of these entities can be considered as sources for inputs into the system and destinations of outputs from the system. Two, interactions. These represent the interactions between the external entities and the system and are represented by arrows. Arrowheads represent the direction or flow of the particular interaction. While double-headed arrows are allowed, single-headed arrows communicate clear information to the reader. Thus, the engineer should be careful when using two-directional interactions. Make sure the meaning of your interactions are clear. Regardless, each interaction that is an arrow is labeled to identify what is being passed across the interface. Three, the diagram depicts the common types of interactions that a context diagram typically contains. In an actual context diagrams, these interactions would be labeled with the specific interactions, not the notional words used above. The labels need to be sufficiently detailed to communicate meaning, but abstract enough to fit into the diagram. Thus, the words such as data or communication are to be avoided in the actual diagram since they convey little meaning. For the system, this is the single geographical figure mentioned already. Typically, this is an oval, circle, or rectangle in the middle of the figure with only the name of the system within. No other information should be present. We can categorize what can be passed across these external interfaces by utilizing our definitions of the four basic elements listed above. These elements, using these elements and adding one additional element, we can form 5 categories: data, signals, materials, energy, and activities. Thus, the system interacts with its environment and specifically the external entities by accepting and providing either one of the first 4 elements or by performing an activity that influences the system or the environment in some manner. Constructing a diagram such as the system context diagram can be invaluable in communicating the boundaries of the system. The picture clearly and easily identifies the external interfaces needed and provides a short description of what is being passed into and out of the system, providing a good pictorial of the system's input and outputs. What about the context diagram for an automobile? So we can be thinking of an example. So this is a simple example for a typical automobile. Although the system is rather simple, it nicely illustrates all 5 of these interfaces. 4 external entities are discussed. Users, that is to include the driver and passengers. The maintainer, which could be a user, but because of his specialized interactions with the system is listed separately, an energy source, and the environment. Most systems will interact with these four external entity types. Of course, many other entities may interact with the system as well. The user provides a multitude of inputs to the system, including various commands, controls, as well as actions such as steering and braking. Materials are also passed to the system. Cargo. In return, several outputs are passed from the automobile back to the user, including various status indicators on the state of the system. Additionally, an activity is performed. Entertainment, representing the various forms of entertainment available in today's automobiles. And finally, cargo is returned to the users when desired. Other entities also interact with the system. The maintainer must provide a request for diagnostic data, typically in the form of signals, passed to the auto via an interface. Diagnostic data are returned along with the exchange of parts. The last two external entities represent somewhat specialized entities, an energy source and the ubiquitous environment. In the automobile case, the energy source provides gasoline to the automobile. This energy source can be one of many types: electric, a gasoline pump at a station, or a small container with a simple nozzle. The environment requires some specialized consideration, if for no other reason that it includes everything not specifically contained in the other external entities. So in some respects, the environment entity represents others. In the example, the automobile will generate heat and exhaust in its typical operation. Additionally, a siren and light from various light bulbs, horns, and signals will also radiate from the auto. The environment is also a source of many inputs, such as physical support, air resistance, and weather. It takes some thought to identify the input, output, and activities that are part of a system and a system environment interaction. The creator of the diagram would have really gone overboard and specify temperature, humidity, light, humidity, and a number of other factors in the interaction. This brings up an interesting question. What do we include in listing the interactions between the system and an external entity? For that matter, how do we know whether an external entity should be included in our diagram? Fortunately, there is a simple answer to this. If the interaction is important for the design of the system, then it should be included. In our automobile case, physical support is important for our design and will influence the type of transmission, steering, and tires, so we include support in our diagram. Temperature, humidity, pressure, etc. will be a factor, but are not sure about their importance to the design, so we group these under characteristics under weather. This does not mean that the automobile will be designed for all environmental conditions, only that we are not considering all conditions in our design. We should have an idea of the environment condition from the requirements, and therefore we can determine whether they should be in our context diagram. Output from the system to the environment also depends on whether it will influence the design. The automobile will, in fact, output many things into the environment: heat, smells, texture, colors, and especially carbon dioxide as part of the exhaust. But which of these influences our design? 4 will be major influences: heat, noise from the siren, exhaust, and light. Therefore, we include only those 4 for now and omit the others. We can always go back and update the context diagram. And in fact, we should, as we progress through both the system engineering process and the system development lifecycle. The system context diagram is a very simple yet powerful tool to identify, evaluate, and communicate the boundaries of our system. Therefore, it becomes the first tool we introduce in this book. More will follow that will eventually provide the system engineers with a collection needed to adequately develop the system. Note that in model-based system engineering, MBSE, style guides and model practices in a given organization should facilitate the development of the system context diagram. For example, a guideline that any entity defined as a use case diagram, which is one of the diagram types that is part of the system modeling language, must be a proper property in the system context that ensures complete traceability between the behavior, explorations, and the context. As the context is further defined in the system model, inputs and outputs can be modeled and flows can be established between elements that is associated with specific interfaces. Validation rules and automated quality checks can ensure this consistency, allowing the system engineer to focus on cognitive tasks instead of the administravia of cross-checking diagrams and other content. Well, next, let's talk about environments, the type of environmental interactions. To understand the nature of the interaction of a system with its surroundings, it is convenient to distinguish between primary and secondary interactions. The former involve elements that interact with the system's primary functions, that is, represent functional inputs, outputs, and controls. The latter relate to elements that interact with the system in an indirect, non-functional manner, such as physical support, ambient temperature, and so on. Thus, the functional interaction of a system with its environment include its inputs and outputs and human control interfaces. Operational maintenance may be considered a quasi-functional interface. Threats to the system are those entities that deny or disrupt the system's ability to perform its activities. The physical environment includes support systems, system housing, and shipping, handling, and storage. Each of these is briefly described next. So in terms of inputs and outputs, the primary purpose of most systems is to operate on external stimuli and or materials in such a manner as to process these inputs in a useful way. For passenger aircraft, the materials are the passengers, their luggage, and fuel, and the aircraft's function is to transport the passengers and their belongings to a distant destination rapidly, safely, and comfortably. As we're showing here in this figure, it illustrates some of the large variety of interactions that a complex system has in its operational environment for the case of a passenger aircraft. For system operators, as noted previously, virtually all systems include automated systems, do not operate autonomously, but are controlled to some degree by human operators in performing their function. For the purposes of defining the systems engineer's task, the operator is part of the system's environment. The interface between the operator and the system, that is the human-machine interface, is one of the most critical of all because of the intimate relationship between the control exercised by the operator and the performance of the system. It is also one of the most complex to define and test. In terms of operational maintenance, the requirement for system readiness and operational readiness, reliability relate directly to the manner in which it is to be maintained during its operational life. This requires that the system be designed to provide access for monitoring, testing, and repair requirements that are frequently not obvious at the onset, but nevertheless must be addressed early in the development process. Thus, it is necessary to recognize and explicitly provide for the maintenance environment. Threats. This class of external entities must be man-made or natural. Clearly, weather would be considered a threat to a system exposed to the elements. For example, when an engineered naval system, the saltwater environment becomes a corrosive element that must be taken into consideration. Threats can also be man-made. For example, a major threat to an automated teller machine, ATM, would be the thief, whose goal might be to access the stored cash. System threats need to be identified early to design countermeasures into the system. Support systems. Support systems are the part of the system infrastructure on which the system depends for carrying out its mission, as shown in the figure. The airport, the air traffic control system, and their associated facilities constitute the infrastructure in which an individual aircraft operate, but which is also available to other aircraft. These are parts of the system of systems represented by the air transportation system, but for an airplane, they represent standalone available resources. Two examples of common support systems that have been mentioned previously are the electric power grid, which distribute usable electric power throughout the civilized world, and the network of automobile filling stations and their suppliers. In building a new airplane, automobile or other system, it is necessary to provide interfaces that are compatible with and capable of utilizing these support facilities. System housing. Most stationary systems are installed in an operating site, which itself imposes compatibility constraints on the system. In some cases, the installation site provides protection for the system from the elements such as variations in temperature, humidity, and other external factors. In other cases, such as installations on board ship, these platforms provide systems mechanical mounting, but otherwise may expose the system to the elements such as the subject to the shock, vibration, and other rigor. For shipping and handling environment, many systems require transportation from the manufacturing site to the operational site, which imposes special conditions for which the system must be designed. Typical of these are extreme temperature, humidity, shock, and vibration, which are sometimes more stressful than the characteristics of the operating environment. It may be noted that the impact of the latter categories of environment interactions are addressed mainly in the environmental development stage. In terms of interfaces and interactions, first, let's think about the interfaces of both external and internal. The previous section described the different ways in which a system interacts with its environment, including other systems. These interactions all occur at various boundaries of the system. Such boundaries are called the system's external interfaces. Their definition and control are a particular responsibility of the system engineer because they require knowledge of both the system and its environment. Proper interface control is crucial for successful system operation. A major theme of systems engineering is accordingly the management of interfaces. This involves 1, identification and description of the interfaces as part of the system concept definition. 2, coordination and control of the interfaces to maintain system integrity during engineering, development, production, and subsequent system enhancements. Inside the system, the boundaries between the individual components constitute the system's internal interfaces. Here, again, the definition of internal interfaces is the concern of the system engineer because they fall between the responsibility boundaries of engineers concerned about the individual components. Accordingly, their definition and implementation must often involve consideration of the design trade-offs that impacts on the design of both components. Particular complexity for the system engineer requiring close attention are the interfaces that occur in network systems. Often these are hidden in embedded software or secondary interactions that are not easily visible beyond the system components. Unexpected failure or the introduction of rogue software during operation can further challenge system designs in information systems needing protection from undesired external interfaces. Next, let's talk about interactions, both functional interactions and physical interactions. Interactions between two individual elements of the system are affected through the interface connection connecting the two. Thus, the interface between a car's driver hands and the steering wheel enables the driver to guide, that is, interact with the car by transmitting a force, and in turn causes the steering wheel to turn and thereby the car's wheels. The interfaces between the tires of the car and the road both propel and steer the car by transmitting driving traction to the road and also helping cushion the car body from the roughness of the road surface. The above examples illustrate how functional interactions, that is either guiding or propelling the car, are affected by physical interactions, turning the steering wheel or the driving wheels that flow across physical interfaces. The figure that we're showing here illustrates a similar relationship between physical interfaces involved in steering an automobile, an air vehicle, and the resulting functional interactions. An important and sometimes less than adequately addressed interaction, an important and sometimes less than adequately addressed external system interaction occurs during system maintenance. This activity necessarily requires access to a number of vital system functions for testing purposes. Such access calls for the provision of special test points of the system, which can be sampled externally with a minimum of manipulation. In some complex systems, an extensive set of built-in test, or BIT, is incorporated, which may be exercised while the system is in the operational status. The definition of such interfaces also the concern of the systems engineer. In terms of interface elements, to systematize the identification of the external and internal interface, it is convenient to distinguish three different types: connectors, which facilitate the transmission of electricity, fluid, force, and so on between components; isolators, which inhibit such interactions; three, converters, which alter the form of the interaction medium. These interfaces are embodied in components, parts, or subcomponents, which may be throughout be thought of as interface elements. The table that we're showing here illustrates a number of the common examples of interface elements of each of the three types for each of the four interaction mediums: electrical, mechanical, hydraulic, and human. The table brings out several points worthy of note. One, the function of making or breaking a connection between two components, that is, enabling or disabling an interaction between them, must be considered as an important design feature often involved in system control. Two, the function of connecting non-adjacent system components by cables, pipes, levers, and so on is often not part of a particular system component. Despite their inactive nature, such conducting elements must be given special attention at the system level to ensure that their interactions are correctly configured. Three, the relative simplicity of the interface elements belays their critical role in ensuring system performance and reliability. Experience has shown that a large fraction of system failures occur at interfaces. Assuring interface compatibility and reliability is a particular responsibility of the system engineer. In terms of model-based system engineering and interfaces, or MBSE, in general, what this is developed in the systems modeling language supports the effective and efficient management and definition of interfaces. Components modelers can leverage the modeling tools to prohibit illegal flows detect inconsistencies, and generate detailed interface specifications, whether in the model or an exported document. This ensures consistency and eliminates a common source of error in document-intensive methods, in which engineers are required to read and analyze and disconnected documents without automated support. In a particular well-suited to integrate and analyze subsystem models, perhaps created by different suppliers or departments, connecting the subsystem model interface and executing quality checks to ensure flows out of subsystem A and inputs into subsystem B and vice versa is relatively trivial and significantly less effort than performing this task manually. It should be noted that structuring the models correctly to support these analyses is not trivial, but the payoff in fidelity and reduced subsequent efforts is why model-based system engineering is in COSE's, the system engineering organization, desired pathway forward for system engineers. In terms of complexity in modern systems, early in this chapter, we describe the system hierarchy, how systems are divided into subsystems and components, subcomponents, and finally parts. You can refer back to an earlier table that showed that as modern systems grow in complexity, the number, diversity, and complexity of these lower level subsystem components and parts increases. Furthermore, the interaction between these entities also increases in complexity. System engineering principles and their applied practices are designed to deal with the complexity. Increasing a single system may be or become a part of the larger entity. While there are many terms currently in use today to describe this super system concept, the term system of system, SOS, seems to be accepted by a wide variety of organizations. Other terms are found in the literature, some meaning the same thing, some have different connotations. Details will be provided later in a later chapter. Another concept, enterprise system engineering, refers to the application of system engineering principles and practices to engineering systems that are part of an enterprise and will be discussed in another chapter. Then there are families of systems that are related in various ways. The next section provides a basic introduction to the engineering of entities that are considered, quote, above or more complex than single systems, systems of systems, enterprises, and families. So this is just a brief summary of that. So we're thinking about system of systems. For our purpose, we will use two definitions to describe what is meant by a SOS. Both come from the U.S. Department of Defense, from a 2008 reference. The first is the simplest, a set of arrangements of systems that results when an independent and useful systems are integrated into a larger system that delivers unique capabilities. In essence, anytime a set of independently useful systems is integrated together to provide an enhanced capability beyond that of the sum of the individual systems' capabilities, we have a SOS, system of systems. Of course, the level of integration could vary significantly. At one end of the spectrum, SOS could be completely integrated from the earliest development phases, where the individual systems, while able to operate independently, are almost exclusively designed for an SOS. At the other end of the spectrum, multiple systems could be loosely joined for a limited purpose and time span to perform a needed mission with no more than an agreement of the owners of each system. Thus, a method to capture the range of integration is necessary to fully describe the different nuances of systems of systems. As a reader might surmise, engineering and architecting an SOS can be different than engineering and architecting a single system, especially for two middle categories. System of system engineering, SOSI, can be different because of the unique attributes of a SOS. So thinking about system hierarchy, let's first of all focus on enterprise system engineering, or SOCI. By nature increases the complexity of developing single systems. However, it does not represent the highest level of complexity. In fact, just as a table we talked about earlier presented a hierarchy with the system at the apex, we can expand this hierarchy and go beyond systems of systems. We can go to an enterprise. And so now in this figure, we're depicting that hierarchy. Above an SOS lies the enterprise, which typically consists of multiple systems of systems within its structure. Furthermore, an enterprise may consist of a varied collection of system types, not of all which are physical. For instance, an enterprise includes human or social systems that must be integrated with physical systems. Formally, an enterprise is, quote, anything that constitutes consists of people, processes, and technology, systems, and other resources across organizations and locations interacting with each other and their environment to achieve a common mission or goal, end of quote. The level of interaction between these entities varies, just as component systems within an SOS do, and many entities fit into this definition. Almost all mid-sized to large organizations would satisfy this definition. In fact, sub-organizations of some large corporations would themselves be defined as an enterprise. Government agencies and departments would also fit into this definition. And finally, large social and physical structures such as cities or nations satisfy this definition. The source of complexity in enterprise system engineering is primarily the integration of the diversity of systems and processes. The enterprise typically includes the following components that must be integrated together under their inherent uncertainty of today's enterprise: business strategy and strategic planning, business processes, enterprise services, governance, technical processes, people management and interactions, knowledge management, information technology, infrastructure and investments, facility and equipment management, supplies management, data and information management. Enterprise system engineering refers to the application of system engineering principles and practices to engineering systems that are part of an enterprise. Developing the individual component systems of the enterprise is known by this term. Another broader term has emerged: enterprise engineering. This term, with the systems omitted, typically refers to the architecting, development, implementation, and operation of the enterprise as a whole. Some have used this term interchangeably. However, the two terms refer to different levels of abstraction. The reason that enterprise system engineering is deemed more complex than SOCI is that many of the components of an enterprise involve one or more systems of systems. Therefore, the enterprise could be considered an integration of multiple systems of systems. Just as new tools and techniques are being developed for SOCI applications, so too are tools, methods, and techniques being developed for this relatively young field. For a family of systems, in some circumstances, it is helpful to identify a particular group of systems. The members of a family of systems, or FOS, have a common characteristics, but the grouping does not provide a new capability, and they may not be connected into a whole. An FOS family of systems may be a product line or a set of systems used in a common environment. The set of systems would be a group of independent, not independent, systems that can be arranged or interconnected in various ways. The family of systems would be a set of manned or unmanned vehicles, a group of space satellites, or a family of network systems. Such arrangements would not present new properties or capabilities, and they lack the synergy of a SOS system of systems. Okay, in summary, let's consider these things one at a time. So system building blocks and interfaces: the need for system engineers to attain a broad knowledge of several interacting disciplines involved in the development of a complex system raises the question of how deep that understanding needs to be. For the hierarchy of complex systems may be represented by a hierarchical structure in that they are composed of subsystems, components, subcomponents, and parts. The domain of a system engineer extends down through the component level and extends across several categories. In contrast, the domain of the design specialist extends from the part level up through the component level, but typically within a single technology area of discipline. For system building blocks are at the heart of components and are the basic building block of all engineered systems, characterized by both functional and physical attributes. These building blocks are characterized by performing a distinct and significant function and are singular. They are within the scope of a single engineering discipline. Functional elements are functional equivalents of components and are categorized into 4 classes by operational medium. Signal elements, which sense and communicate information; data elements, which interpret, organize, and manipulate information; material elements, which provide structure and process material; engineering elements, which provide energy or power. Components are physical embodiments of functional elements, which are categorized into 6 classes by materials of construction: electronic, electro-optical, electromechanical, mechanical, thermomechanical, and software. System building blocks models can be used to identify actions capable of achieving operational outcomes, facilitate functional partitioning and definition, identifying subsystem and component interfaces, and visualizing the physical architecture of the system. The system environment, the system environment, that is the environment outside of the system that interacts with and includes system operators, which are part of the system function, but outside of the delivered system. 2, maintenance, housing, and support systems. 3, shipping, storage, and handling. 4, weather and other physical environments. And 5, threats. In terms of interfaces and interactions, interfaces are a critical system engineering concept which affect interactions between components and can be classified into 3 categories: connect, isolate, or convert interactions. They require identification, specification, coordination, and control. Moreover, test interfaces typically are provided for integration and maintenance. And finally, complexity in modern systems. Each system is always part of a larger entity. At times, that this larger entity can be classified as a separate system in itself beyond simply an environment or, quote, nature. These situations are referred to as, quote, systems of systems. They tend to exhibit several distinct characteristics: operational independence of the individual systems, managerial independence of individual systems, geographic distribution, emergent behavior, evolutionary development, self-organization, and adaptation. Enterprise system engineering is similar in complexity, but focuses on organizational entity. Since an enterprise involves social systems as well as technical systems, the complexity tends to become unpredictable. All right, well, thank you very much.